Okay, so I'm going to go ahead and get started here. And the first thing I would like to do is just point out that the sine curve, which I'm sure you're very familiar with, kind of oscillates like this. In this particular problem, we are looking at starting from 0 and going to 2 pi. So that means we're going to start here at 0 and we're going to end here at 2 pi. And probably just using mental math, you can tell that the slope of the secant line there would be 0. So we are interested in figuring out if the mean value theorem applies here. Well, the first question is this function continuous? And clearly it is. And is it differentiable? And clearly that is also true as well. And you guys should hopefully know that the derivative of sine is cosine. The other thing you could argue is that this is a nice, smooth, continuous curve with no sharp turns or asymptotes or anything like that. So it does apply in this situation. So we need to see if we can find the values c. That's just a fancy way of saying the x values for which this would be true. And since we know that the slope of the secant line is 0, then we just need to figure out where the slopes of the tangent lines would be 0. And if we think about the graph, that would be here and that would be here. Or if we want to use the derivative, f prime of sine would be the cosine function. And then ask yourself, when is the cosine function equal to 0? And the cosine function is equal to 0 when c is equal to pi over 2 and 3 pi over 2. So those are the two c values for which the mean value theorem would be true. And then number 3, how could this problem be connected to Rolle's theorem? Well, it could be connected to Rolle's theorem simply because in this case, the slope of the secant line and the slope of the tangent line are 0, and that is exactly the subcase that we call Rolle's theorem. So I could have actually just changed this problem to Rolle's theorem and not refer to it as the mean value theorem. Does anybody have any questions on the warm-up? And again, this is just to kind of get you, this is what we did last week, so I thought this might be a good place to start. Okay, so let's go ahead and look at today's content. And again, today we're going to look at something called curve sketching. And curve sketching is just a fancy way of saying analyzing a curve without technology. In other words, knowing where maximums are, where asymptotes are, where concavity changes, all kinds of things like this without the use of technology. And by the way, we should note here that even in this graph on the warm-up, I used Desmos to graph this curve. Now, I hope that you guys have this curve memorized, but if I gave you some more interesting function, you may not know what it looks like. So here's a function, and oh, I should mention this. If you want this presentation, please just send me an email, and I will be glad to send it to you. This is different than the problems I did in the video that's already posted on Canvas. So here's our function. It's k of t is t squared minus 6t plus 12 divided by t over 4. By the way, I'm also assuming that you've watched my video. So I'm cutting out quite a bit of the content, and we're just going to focus on a couple of things, a couple of problems. Number 1, the domain. We want to figure out what the domain of this function is. And since this is a rational function, we need to be careful for any places where this function would not be defined. And it looks like the only place that this function would not be defined would be when the denominator value of t is equal to 4, because t minus 4 is 0. So I'm going to say that the domain is all real numbers not equal to 4. In other words, we can put any real number in here that we want, and our function will be perfectly well defined, except for the case of 4. X-intercepts. Now, this goes back to Algebra 1 or Algebra 2. To find an x-intercept, what we want to do here is we're going to let y equal 0. In other words, this here would be equal to 0, and we would try to figure out where this function would be equal to 0. And the way that you would do that is you would look at the denominator here. So then you would have t, looks like it's going to be, and let's make sure that we don't make any careless mistakes here. We just need to factor this numerator. So we got to think of two numbers that have a product of 12 and a sum of negative 6. And the answer is there are none. And the reason that there's none is because if we look at the discriminant of this, which is b squared minus 4ac, it turns out to be less than 0. That means that that would be the only solutions for that particular polynomial would be imaginary numbers. And in calculus, at least at this level, we are not going to be concerned with that. So I can tell you right now that this function does not cross the x-axis. To find the y-intercepts, we need to let x equal 0, or in this case, I should say t equal to 0. And if I let t equal to 0, you're going to quickly see that this will all be 0, and we're left with this 12 over negative 4. So it looks like our y-intercept, or here I guess I should maybe call it our k-intercept, if you will, is going to be k, or let me just write that as an ordered pair. That might be a better way of doing that. Let me erase all of this stuff here, get this out of the way. Let's just go ahead and let that be k. That's going to be 0, negative 3. Okay, so when I plug 0 in for t, these are all zeros. You're going to get with 12 and over negative 4. Okay, so that's going to be our y-intercept, if you will, in this particular problem. Now I'm going to skip to the next slide. The next two things I'm going to do is I'm going to look at symmetries and asymptotes. And by the way, so far everything we've done, you guys would agree, this is more algebra 2 stuff. But I am reviewing it because I have found that even students that are in calculus sometimes forget these things. All right, so again, I would be willing to share this slide with you if you'd like it, but there are 3 symmetries that you should know. One of those is a symmetry with respect to the y-axis, and a symmetry with respect to the y-axis, you plug negative x into the equation, and hopefully you will get out the exact same equation, and that would be a symmetry with respect to the x-axis. A symmetry with respect to the x-axis, you're going to replace the y with a negative y, and hopefully you'll get an equivalent equation. And then the third option is to get an origin symmetry, which is what I have down here. This is actually an example of an origin symmetry. It turns out if you plug negative x and negative y into this equation, you will get the exact same equation out, which will let you know that this particular example, which by the way has nothing to do with the example that we're doing here today in class, is exactly the same equation. So if we go back to our problem here, if we plug negative t in, it turns out that that is not true. If we plug negative k in, that turns out to be not true. And if we plug negative t and negative k in, that also turns out to be not true. So unfortunately, in this example, there is no symmetry. This particular curve is not symmetric with the x-axis, the y-axis, or the origin. Next up is asymptotes. And I want to spend a minute reviewing these because this is actually the first thing where we actually get into calculus. Hopefully you recall that the definition of a vertical asymptote is when the limit of a function approaches infinity. So if I said that the limit as x goes to, let's say, I don't know, 4 of f of x, if that was equal to infinity, then that would be what we would call a vertical asymptote. If I'm interested in horizontal asymptotes, by the way, this is all in chapter number 1. This is chapter number 1. It turns out if the limit as x goes to infinity of the function is equal to, let's say, 7, that will give us a horizontal asymptote. And then the last thing I got a real quick poll question here I'd like to ask you guys. Hopefully you guys know where the polling questions are. And I will post that right now. And all you need to do is say yes or no. And that question revolves around slant asymptotes. And I'm going to go back to our initial slide here. I'll give you a second to answer that question. Okay, so most of you do not know how to find slant asymptotes. So that goes back to algebra 2. So you may not remember that. That was a couple of years ago. So I will go over slant asymptotes. It turns out that this curve has a vertical asymptote at 4, which you probably could have guessed since that was already restricted in the domain. That's a pretty good indication. It actually does not have any horizontal asymptotes. In other words, if I take the limit of this function to infinity, I do not get a number. I get infinity or negative infinity. And it does have a slant asymptote of t minus 2. So let me explain that real quick. I'm going to clear up a little bit of room here on my screen. I'm going to get rid of this here. Okay, to find a slant asymptote, all you do is you do polynomial long division. So you're just going to do t squared minus 6t plus 12, and you're just going to divide that by t minus 4. So hopefully this is something that you recall from pre-calc or algebra 2. So t goes into t, well, t times. So t times t is t squared. T times negative 4 is negative 4t. And then we need to subtract. And when we subtract here, we're going to get negative 2t plus 12. You bring down the 12. What times t gives you negative 2t? Well, that'd be negative 2. So then this is going to give you negative 2t. And then that's going to be, what, positive 8. Again, you're going to subtract. The remainder here is going to be 4. This is our remainder. But hopefully you'll recognize that this quotient gives you the equation for the slant asymptote. Now, if you don't remember that, that might be something to make note of, because I actually find slant asymptotes very helpful when it comes to analyzing curves. I might pause here because now I'm going to go to a completely different slide and start doing more calculus-y type things. Most of this was review of Algebra 2 and pre-calculus. Does anyone have any questions or comments at this point? Okay, so if you do, again, feel free to unmute yourself, or if you want, you can just type something in the chat. I'll try to listen for that. Okay, I'm going to go ahead and move on. By the way, I haven't done anything yet really in terms of graphing this thing. That's what we're trying to do. So there we go. So now we're going to go to the calculus-y part of this. And so I've kind of cheated here a little bit to speed up the process. I've already went ahead and taken the liberty of giving you guys the derivatives, okay? And again, if these derivatives get cumbersome for you or difficult, I would actually prefer you to use, when you're practicing or doing homework, feel free to use Wolfram Alpha to help speed up that process. So let's go ahead and talk about critical numbers here. So there's the first derivative, and I want to find the critical numbers. So remember, critical numbers is where k prime is equal to 0 or d and e. And in this case, I only need to worry about the numerator. So it looks like we have critical numbers of 2 and 6. Those are the only two critical numbers. Please don't say that 4 is a critical number. 4 is not I'm just going to tell you, 4 is not a critical number because it's not in the domain. And since 4 is not in the domain, it cannot be a critical number. In other words, it cannot be an extreme value. So here's our critical numbers. Now we can start looking at where this thing increases or decreases. So then what we want to do here is I'll just call this my K prime graph, and I'll put my two critical numbers, and this should hopefully seem like review. And once we do that, we're going to see that when we plug values of less than 2 into the function, we're going to get positive. Numbers between 2 and 6, we're going to get negative, and then we're going to get positive. That tells us it's increasing here, decreasing there, and increasing there. So we know that the function is increasing from negative infinity to 2, and it's increasing from 6 to infinity. It's decreasing from 2 to 6. Technically, you could argue that it's decreasing from 2 to 4 and 4 to 6, but I'm just going to write 2 to 6. Also, based on this chart here, we can clearly see that there are two extreme values, and those extreme values are at 2 and at 6. At 2, it's going to be a relative max because K prime changes from positive to negative. So I'm going to say that there is a relative max, and it turns out to be a y value of negative 2 there. And to get that negative 2, I would have plugged 2 into the original function. We also know that we have a relative min at 6, and the corresponding y value in that case turns out to be 6. And the reason that that is a relative min is because the derivative changed sign from negative to positive at 6. So we get critical numbers, increasing, decreasing, and relative extrema from the first derivative. Now let's go ahead and look at concavity. Remember, concavity and points of inflection are based on the second derivative. So if we look at the second derivative here, we could play the exact same game. Now, I'm going to draw another graph. And on this graph, the only number I'm going to put on here is 4. Now, you might say, well, wait a minute, Mr. Allen, you told us just a minute ago that 4 is not a critical number. It is not a critical number of the first derivative. It is a critical number of the second derivative. In other words, the concavity can change at 4. Can we have a POI at 4? Well, the answer is no. You can't have a POI at 4 because, again, 4 isn't in the domain. Now, it turns out that this is concave down over here, and it is concave up over here. And again, what you would do to figure out if it was concave, well, let's just do the concave up here. That'll be very easy. A number bigger than 4 might be 5. When you plug 5 into the second derivative, you're clearly going to get positive over positive. That's positive, therefore it's concave up. So that tells us that it is concave down from negative infinity to 4. And then it is, oops, not that. And then it is concave up from 4 to infinity. Now, the only place that this could have a point of inflection would be at 4, but that's not possible because 4 is not in our domain. So there is none or no points of inflection in this particular example. So now let me go ahead and summarize all the things that I've done in this problem. I did a whole bunch of pre-algebra types, or not pre-algebra, pre-calculus type stuff here on this slide, although the asymptotes, you could argue, are calculus-based things. This other stuff is more Algebra 2 pre-calc. And then on this slide, I've done a whole bunch of calculus things. And this is what we call analyzing a curve. And so now what we can do is we can actually use all that information to sketch the graph of this curve without technology. So the first thing that I would do is I would include my asymptotes. And we know that we have an asymptote at t equals 4. And we also know that we have a slant asymptote. Oops. We have a slant asymptote at k equals t minus 2. Now, these asymptotes help us very much with our graph. So now what I'm going to do is I'm actually going to use the information from the previous 2 slides. And I'm going to cheat a little bit because I obviously have done this problem before class. But this is what the curve is going to look like. In fact, some of you may have already graphed it with your graphing calculator. And if I remember correctly, I think we said we had a point, a relative maximum right here at, I think it was 2, -2. And then I think up here we had a relative minimum at, I think it was 6, 6. And I'm not going to go through all of the details, but we can clearly see that this is concave down to the left of 4. It's clearly concave up to the right of 4. We can see that we have a vertical asymptote, we have a slant asymptote, and this is what the graph will look like. And if you want to check that with your graphing calculator, that you can. But I claim that you can do all of these things without technology, with just knowing your pre-calculus algebra 2 skills. And now with calculus, we can add to that by using things like points of inflection, which this one does not have an example of, but we do have this relative max, and we have a relative min here using the first fundamental theorem of calculus. The first derivative test. And so there's our curve. So this is curve sketching. And everything I did prior to this slide is me analyzing the curve. That means me digging into the curve and figuring out properties of that curve. Now, I want to go ahead and talk a little bit of why we care about this. So who cares? Well, here's the first thing that you need to keep in mind. When you take the AP exam in May, there will be half the test will be calculator and half the test will be no calculator. So if you're dealing with a no calculator part of the AP exam, this process can help you analyze curves that you may not be familiar with. Number 2, did you know that in some universities, like Purdue University, guess how many calculators you're allowed to use on their tests? 0. Purdue University does not allow math students to use calculator on any of their assessments, which, by the way, is a very strong engineering and school that most of you might be familiar with. Number 3, have you ever plugged a function into your calculator and accidentally plugged it in incorrectly? I bet you have. And I don't know if you noticed, I don't know if it was this class, but I remember one class last week, I was doing something, and as soon as I wrote something down, I knew I did it wrong. How did I know I did it wrong? Well, I knew I did it wrong because I know the calculus and the mathematics behind the problem, and I knew whatever it was that I did with my calculator had to be incorrect. So these are some of the reasons why you need to be able to do this. Okay, so questions so far. This would be a great time for me to stop. I've got one more example I'm going to do after this, but does anyone have any questions on that last problem or anything I've done so far? I'm going to go back to this graph. Okay, well, I'm going to go ahead. You can stop me if you need to, but I'm going to go ahead and go to the next one. Now, I'm going to go a little bit slower on this one, and I'm going to actually encourage you to maybe try to get ahead of me on this problem, preferably without your calculator. I'm just doing, this is the last problem, and I would predict that most of you do not know what this curve looks like. The last one, you maybe could have had an idea of what it looked like. I did that one on purpose because it had a slant asymptote. But this one here involves cosine and sine, and then a quotient of those two things. So I'm just curious if any of you would even have any idea what that would look like. And my guess is you probably wouldn't. And so let's pretend that this is the AP exam or my test or something like that, and you had to somehow figure stuff out about this without technology. Now I'm going to try to go slow. I'm giving you a little bit of a head start here. I'm going to do all the pre-calculusy stuff here in a second. Hopefully you've got that curve written down. I'm also going to go ahead and show you the derivatives if you want those. So the derivative of that function is -1 over 1 plus sine theta. And the second derivative is cosine theta over quantity 1 plus sine theta squared. So you can tell I probably use the quotient rule for those derivatives, and you can trust me that those are correct. So we're going to try to analyze and sketch the graph of this curve. And by the way, we're going from, we're not going to go ahead and use all the real numbers. We're just going to go from -2 pi to 2 pi. All right, I'm going to go ahead and get started. So it turns out, again, just like in the first example, the only thing that we need to be concerned about with the domain is when is this going to be 0? When is 1 plus sine theta going to be equal to 0 on this particular domain? In other words, when is sine of theta equal to -1? That's where we're going to have issues with the domain. Does anybody happen to know where sine is equal to -1? Well, I'll just tell you. I'm sorry, guys. I want to just interact with you guys, but now you guys are on the other side of the screen there. So the domain here turns out to be all theta not equal to -pi/2 and 3 pi over 2. As long as theta does not equal those two values, we're good to go. Those are the only two that are going to blow this thing up, because if you put those in, you are going to get a denominator equal to 0. Okay, so to figure out the x-intercepts, in fact, I'll show my work over here. X-intercepts, remember, you let this side equal to 0. So that would be cosine theta over 1 plus sine theta. And then you would need to solve this. When is this equal to 0? Well, that's only going to be equal to 0 when cosine of theta is equal to 0. So the x-intercepts here turn out to be -3 pi over 2 and pi over 2. These are the x-intercepts, and they're technically not x-intercepts. We're going to call them theta-intercepts. And you'll notice that there's kind of a connection between these two things here. In terms of y-intercepts, to find a y-intercept, to find a y-intercept, we're going to let theta equal 0. So that's going to be f equals the cosine of 0 over 1 plus the sine of 0. Well, the sine of 0 is 0, so you're essentially saying the cosine of 0, and the cosine of 0 is 1. So that's going to be our y-intercept. So I'm going to say that f of theta is equal to 1, or you could, better yet, let me write it this way. It's going to be 0, 1. That is going to be your y-intercept, 0, 1. In terms of symmetries, and again, I apologize, this isn't maybe the greatest example because this one has no symmetries. Symmetries can be helpful. If you know it's symmetric with respect to the y-axis, then you know the left side equals the right-hand side. And then you, like for example, the cosine curve is symmetric to the y-axis. So you can just basically sketch the right-hand side and you'll know what the left-hand side. Okay, so now we got to deal with asymptotes. And remember, to do a vertical asymptote, we need to figure out where the limit goes to infinity, what values of theta. And in this case, we're going to see that these two guys come back down into play. So we have vertical asymptotes at theta equals negative pi over 2 and 3 pi over 2. And we could talk about one-sided limits here, but I'm going to go ahead and skip that just to kind of keep this on the shorter side. In terms of horizontal asymptotes, a horizontal asymptote, we would have to take the limit of this function as theta goes to infinity, which does not exist. So there are none. There are no horizontal asymptotes. It also turns out that there are no slant asymptotes. I should probably let you know that there's certain restrictions on slant asymptotes. It is in the book, and I'll mention it here briefly. Basically, you're going to get slant asymptotes when you're dealing with a polynomial function divided by a polynomial function, and the degree of the polynomial on the numerator has to be one more than that of the denominator, and that's when you'll get slant asymptotes, like we saw in our first example. This is not a polynomial function, and we do not end up with any slant asymptotes. Comments or questions here for this particular example so far? Again, I haven't really gotten too much into any calculus-y stuff. This is more pre-calc. Okay, so let's go ahead and finish this guy off. So I've got the first derivative here. Here's the first derivative. So what are going to be my critical numbers here? What are going to be the critical numbers? So remember, critical numbers, this is where f prime is equal to 0 or d and e. F prime is equal to 0 or d and e. And in this case, there are none. There are no critical numbers. And that's very interesting. That actually tells us that this curve has no extreme values. Does it have a min, and it does not have a max anywhere. So that's kind of interesting. Now we want to try to figure out where it is increasing or decreasing. Well, guess what, guys? There are no critical numbers. So basically all you've got to do is plug in any number you want into here. I'm just going to plug in, let's say 0. So I'm going to plug in 0 into this because this is my f prime graph. There's no critical numbers on it. So I'm going to plug in 0. So if I plug in 0 here, the sine of 0 is 0. So I get negative 1 over 1, which is negative. And guess what that tells us? This function is decreasing everywhere. Every part of this function is going to be less than 0. So it's going to be decreasing everywhere, or all real numbers from negative infinity to infinity. Extrema, well, we can already answer that. There's none of those. I've already mentioned that because there are no critical numbers. Now let's go ahead and look at the second derivative. The second derivative is a little bit more difficult to deal with. And we need to be worried about when this is equal to 0, that is the numerator. We also need to be concerned when the denominator is equal to 0. And it turns out that we've actually already seen all of those values before this particular part of the problem. So if we look at the second derivative here, we're going to get negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Now, again, we've already established that there are no extrema. However, if we look at the second derivative, there are things that could make this denominator equal to 0, and there are things that will make this numerator equal to 0. And it turns out that this one alternates between positive, negative, and I think I left off 0. I think 0 might need to be in here as well. Nope, it doesn't. So then this is positive, this is negative, and then this is positive. So it's going to be concave up here, concave down here, concave up here, concave down here, and then concave up there. So concave up from negative infinity to negative, 3 pi over 2 union negative pi over 2 to pi over 2 union 3 pi over 2 to infinity. That's where it's concave up. It is concave down at negative 3 pi over 2 to negative pi over 2. And it is also concave down from pi over 2 to 3 pi over 2. And then the last thing we want to talk about here is points of inflection. Well, let's see here. At negative 3 pi over 2, is our function defined there? Well, if we go back to the last part where we looked at the domain, is it defined at negative 3 pi over 2? The answer is yes. So guess what that makes this point right here? This is going to be a point of inflection. All right, notice it went from concave up to concave down. But now let's look here at negative pi over 2. Is that a point of inflection? Well, again, if we look back at the beginning, is negative pi over 2 in our domain? It is not in our domain, therefore it cannot be a point of inflection. This also turns out to be a point of inflection. I almost said a place of inflection, but that's not the case. And we do not have a point of inflection at 3 pi over 2 because, again, these two guys right here are not in domain. Since they're not in the domain, they cannot be points of inflection. So we have 2 points of inflection, and those points of inflection are negative 3 pi over 2, 0, and pi over 2, 0. All right, so now I've done all the calculus-y stuff, and again, you'll notice that I kind of skipped the step of worrying about finding the actual derivatives themselves. So now let's go ahead and graph it. Now you'll notice I've already put my vertical asymptotes up here, and I think this was at negative pi over 2, and I think this one here was at 3 pi over 2, and I guess I should put theta is equal to that because those are actually vertical lines, right? So those are our vertical asymptotes. We also know that our curve intersected the y-axis, I think, at 1, if I'm not mistaken. So I'm going to put that point on there. I also know that I have a point of inflection. I think we said we had a point of inflection at pi over 2, if I'm not mistaken. So I'm going to put pi over 2 right there. And I think we said we had another point of inflection over here. This is negative pi over 2, negative pi, negative 3 pi. So here's another point of inflection. I'll put POI here. This is a POI here as well, right there. And this is at negative 3 pi over 2. And I guess I should finally wrap this up here and say that this point here is 2 pi, and then this point right here is at negative 2 pi. And now we can sketch our graph, and I'll do it. Let's do purple. So here's how our graph is going to look. It is going to come down. It's going to cross, and then it's going to asymptotically approach the line theta equals negative pi over 2. Then here in the middle, it's going to do the exact same thing. It's going to come down, it's going to cross, and then it's going to come down, and it's going to, and that's actually horrible, guys. I am apologizing because that is the worst curve I've ever drawn. Let me see if I can do that. Let's see if I can fix it a little bit. Okay. That's a little better, but not great. This should be concave up here. This is concave up, and then this should be concave down here based on our graph. And then the last one here, I think we're just going to get just the the tip of this guy here. This is going to kind of come down like this. And so this is our graph. And we can see that indeed our function is decreasing everywhere. Everywhere. Hopefully we can see that it's concave up here, concave down here, concave up here, concave down here, and then concave up there. And we've got our points of inflection, and that's going to be our graph. So let's see how we're doing on time. We're doing great on time. Okay, so I've got one final thing I need from you guys, but I'll pause here for a second if anyone has any questions on this last one. Now, guys, let me just tell you, I did 2 examples, and it's taken me nearly 40 minutes to do 2 examples. I realize that. These problems take time, and that's why you should notice that your homework, I didn't put 10 or 11 problems on there. I knocked it down some because I do know that these take time. This is each one of these problems is a very good practice in all the things we've been working on in chapter 3. Okay? So that's why this is actually a really good review for things that we've been doing in chapter 3 in terms of concavity, increasing, decreasing, extrema, and all that. Okay, so the last thing I'm going to do, and I'm going to go ahead and stop recording now if that's okay. And I hope I can see where I'm actually recording here somewhere. Okay, there we are. I'm going to stop that now.